Welcome to solverfy.
In this problem on the topic of oscillators, we have to consider a simple pendulum which is 0.5 meters in length and has a quality factor of 350. We want to know how long it will take for the amplitude to decrease by 2/3. Next, we want to know that if we are given the amplitude and the mass of the bob, the energy loss rate of the pendulum in watts. And lastly, if we are told that to stimulate resonance with a sinusoidal driving force, how close should the driving frequency be to the natural frequency of the pendulum? So initially, for a damped oscillator, we know that the amplitude decays according to the equation A is equal to the peak amplitude A0 times E to the power BT minus BT over 2M. We're also given the Q value, and we know this Q value is equal to the mass of the bob times omega naught divided by B. We can use these relationships to find the time for the amplitude to decrease to 1/3 of its original value. So from here we can see that B over M is equal to omega naught, the resonant angular frequency, over Q, which is the square root of G over L divided by Q. And we know that the amplitude A is A0 E to the minus B times the T of 1/3 divided by 2M. And we said this is equal to half the peak amplitude, or 1/3 of the peak amplitude rather, 1/3 A0. So the time that we require, T 1/3, is equal to 2M over B times the natural log of 3, if we take the natural log of both sides of that equation. And so we can write this as 2Q divided by omega naught times the natural log of 3, which is 2 times the quality factor Q divided by the square root of G over L times the natural log of 3. And so since we have the quality factor and we have the length of the pendulum, we can calculate this time. And so this time that it takes the amplitude to drop to 2/3, or to decrease by 2/3, if we substitute our values, is 202 into 350 divided by the square root of 9.8 meters per square second over 0.5 meters. And so calculating, and all of this multiplied by the natural log of 3. So calculating this, we get this to be 173.7 in two significant figures. This is 170 seconds. So it takes 170 seconds for the amplitude to decrease to 1/3 of its peak value. Now in part B, we want to know the energy loss rate of the pendulum in watts. Now the energy is all potential energy when the displacement is at its maximum, which is the amplitude. If we assume that the actual angular frequency is very nearly the same as the natural angular frequency, we see that the energy E is a half K A squared, where A is the amplitude. And we can write this as a half times omega squared times M, and the amplitude can be written as A0 E to the minus BT over 2M all squared. And so we can write this as mg over 2L times a naught squared e to the minus bt over m. And so we have an expression for the energy, and then the energy loss rate. Energy loss rate is dE dt. So we can differentiate this expression with respect to time, and this becomes minus b over m times mg over 2L a naught squared e to the minus bt over m. So if we evaluate this at 0, at t is equal to 0, so we get the initial loss rate, we get this to be minus the square root of g over L divided by Q times mg over 2L, which is simply m into a naught squared over 2Q into g over L to the power of 3 over 2. So if we substitute our values into this, we can find this initial energy loss rate. That's the mass of the bulb, 0.27 kg, times the amplitude, 0.02 meters squared, divided by 2 times q, which is 2 times 350, times the acceleration due to gravity g, which is 9.8 meters per square second, divided by the length of the pendulum, 0.5 meters, all to the power of 3 over 2. And so if we calculate, we get the initial energy loss rate of the pendulum to be 1.3 times 10 to the minus 5 watts. Now, the last part of the problem, part C, asks us to find the closeness to the natural frequency that the driving frequency needs to be. Now, to calculate the frequency spread, we have the angular frequency delta omega over omega naught is equal to the quality factor Q, which means that delta 2 pi f over 2 pi f naught is delta f over f naught, and this must be 1 over q, which means that the frequency spread delta f is the original frequency f naught over the quality factor q, and this is simply omega naught over 2 pi times q, and this simplifies to the square root of g over L over 2 pi q. And so if we calculate the change in frequency, the frequency changes can be calculated as the square root of 9.8 meters per square second times the length of the pendulum, 0.5 meters, divided by 2 pi times q, which is 350. So this gives us the change in frequency to be 2 times 10 to the minus 3 hertz. That's the total frequency change, and so the driving frequency which we require must be within 1 times 10 to the minus 3 Hertz on either side of the resonance frequency.